All right, got a bit of an update on a project now. So as you know, I've been building up this IMSI-like Z80 single board computer, and it works great. It's got front panel switches, LEDs. You can control the system. You can start, stop, single step, examine memory, change memory, do a programmed input, look at program output, play around with it, all that kind of stuff. It also has a USB interface so that you can run a command line debugger to interact with it through a command line. It also has a Wi-Fi connection if you don't want to have a cable hanging off there, and there's a 3.7 volt LiPo inside with a few hours of charge on it. So, you can throw it in your pocket and take it to the beach or something and hang out and write machine code until the sun goes down. So that's all fine and good, but the next question is, what else are you going to do with this? So this latest version, which was the 4-layer PCB, I also added these headers on the side, so you can get to basically all the I/O pins on the Z80, which gives you access to the address bus, the data bus, the memory management signals, so M1, read, write, memory request plus I/O request, and a few others, interrupt controls and so on and so forth. So, obvious thing to do with it at this point is go ahead and hook it up to something. So let's hook it up to the outside world. What should we hook it up to? Well, kind of good first choice might be a terminal. Only downside is I don't have access to a terminal, right? ADM3As, kind of hard to come by these days. So next best thing is, of course, an Arduino. So pulled out an Arduino Nano, and that's hooked up to a couple of proto boards here, which is basically a homemade UART. I don't have a UART chip handy, and so had some chips laying around and basically built up some circuitry to let me do the following. I can run, a client program on a PC, talk to the Arduino through a USB port, and when I hit keystrokes in, say, TIO, or PuTTY or whatever, those keystrokes go into the Arduino. It will translate it into commands that this board will understand to respond to I/O requests from the Z80 in such a way that the Z80 can pick up that character. And when the Z80 wants to send a character, it will basically deposit the bits of that character into one of these registers, and it will set a flip-flop. And the Arduino continually polls that flip-flop. When it finds it set, it reads the character from the register and displays it. Okay, now you got to ignore the fact that I have, a 64-bit multi-core processor running, feeding an Arduino, going through a breadboard of stuff just to interact with, a 4-decade-old piece of hardware. That's not the point. The point is, it's really cool, right? Because if I had a terminal, I could hook it up to this, but this is the next best thing. So that's the basic setup, was to try to hook up a terminal-like system to this, so I could basically send in keystrokes and get back characters from the Z80. So here's, for those who are not phobic of digital logic or hardware in general, here's the interface system that I made. So it's got three pieces. The first piece is going from the Nano, that's the ATmega 328, going from that to the Z80, and details of that, basically, here's a serial in, parallel out shift register. So AT328 doesn't have that many I/O pins. I don't have enough pins to do parallel I/O. So when I want to send a character to the Z80, I basically shift it in one bit at a time, most significant bit first. So I toggle a clock here on D2. I call that D out clock. And as I toggle it, I put the bits of the character I'm trying to send onto this D out line. And that shifts them into the 595, and now they're available on these 8 parallel output lines when the output enable pin is pulled low. All right, so that loads my character in, and then I have to tell the Z80 that my character is ready. Well, all I do is I pull down this one line, which is on D4, pull that low. That's the preset line on a 7474 flip-flop, which will turn on its output Q, and that goes through a tri-state buffer and feeds onto bit 0 of the data bus. Okay, so when I want to send, I basically shift in my data to the register, and I pull this line low. I added an extra feature at the last minute, which is to let me read the value of this flip-flop to see if the previous character has been absorbed. I'm not sure that works the way I expected, but it's an option. On the Z80 side, what does it do? Well, the first thing it does is it reads the status line. How does it do that? It pulls this output low, right? And I'll show you where these signals come from in another 2 pictures. But it pulls the read status line low, which enables these 2 signals to go onto the data bus. It checks bit 0 of the signal that comes in. That's the read status. And if it finds that that bit is set, it means this flip-flop has been turned on, so there's a character ready. And in that case, it will go ahead and pull this read character line low, which enables the outputs of this shift register, which puts these 8 bits onto the data bus, and it pulls those into a register. So ATmega can write a character into the register, set the flip-flop. Z80 checks the flip-flop. When it finds it set, reads the character. And when it reads the character, right, this read character goes low. When it pulses high again, that toggles this clock, which loads in the data value, which is a 0. That automatically clears this this flip-flop. So now it doesn't see a character until we assert the character ready again. Okay, so that's the first piece. Second piece, if the Z80 wants to send to the ATmega, well, first thing it does is it reads this, it puts out a read status signal, pulses that low, which is reading in this signal called in status, right? So in status is a flip-flop, basically will get set when I have a character ready for the AT to consume. Once the AT consumes it, again, same deal. It will read in the character and then pulse this line, which says I'm done reading the character. That will clear the flip-flop. So before the Z80 sends a character, it first checks to see if this flip-flop is set. That's what this read status does. So when you pull read status low, it enables this input status, the flip-flop, to go into bit 1 of the data bus. And it checks that, makes sure it's 0. If it's not, it'll sit there and spin. The Z80 was actually sending characters out too fast for the ATmega to keep up with, because the ATmega is pumping the data in serially. So I had to put in that handshake there. So first it checks to make sure that there's no character waiting to be consumed by the ATmega. And then it pulls the right character low while asserting the character on the data bus. So that loads the character into this parallel in serial out shift register, and then it goes ahead and it pulls this character ready line low, which sets this flip-flop. The ATmega is checking this flip-flop. When it finds it set, it pulses in the data over here 1 bit at a time, builds up the character, displays it, and then when it's done, it raises this D in done line briefly, which will tick this clock, which will load in the data value, which is a 0, which clears the character ready. So that's the handshaking in the other direction. All right, so these signals are generated basically by the I/O request, the read or write, and then one of 4 address bits. So when the Z80 says I/O request and read are both low, that says it's trying to read something from a port. I/O request and write both low, it's trying to write something. So here's an active low read signal, and I simply ORed with A0 or A1 to choose one of these 2 signals. If A0 is low, that's my read character signal. I can achieve that by doing an input from port FE, because if I do that as my port number, when these 2 signals are low, bit 0 of the address bus will be low. That's the least significant bit of this port number, and that'll signify a read character. If I read from FD, that'll activate the read status bit, and then I'll in that case, take these 2 bits and send them onto the data bus. And for writing, if I write to port FB, that brings A2 low, so that's my write character signal. So anytime I output to FB, the contents of the data bus will get loaded into this register. And when I output to F7, that will pull the character ready line low, which will preset this, which will say, hey, there's a character ready. And it doesn't matter what I write to port F7. So that's the whole signaling communication, and that's what's going on in all of this stuff. The proto boards over here are basically managing all of that logic. And that was just kind of the hardware that I had laying around that I could put together into this kind of setup. I put together some demo code yesterday to basically let me send characters into the system, and the Z80 would display them on its programmed output, and then it would read whatever the programmed input switches were, and it would send that ASCII code to the terminal, and it would display that. And that actually worked great, but that's just kind of a proof of concept, right? So I wanted to do something beyond that. So let me show you how this works. First of all, let me show you some of the details here. So first of all, the code running on the Arduino is pretty straightforward, right? So those are the different signals that you saw on the right side of those pages. This is my serial port. Set up the I/O direction, load some initial values, and then the main loop is basically what I just described. See if there's a character coming from the keyboard, and if there is, read it in and then send it to the Z80. And then look for a character from the Z80. If you find that one is available, read it and print it. And this check is not necessary. That was a debug. And then the low-level details to send a character to the Z80, right? First, wait for any pending character to be consumed. So spin here until that line goes low. And then basically just loop through all 8 bits and your character with the appropriate bit mask. Set your output bit accordingly and pulse the clock. And then pulse the character ready line low and high to preset that flip-flop to tell the Z80 that a character is ready. And then on the other direction, see if a Z80 character is ready. That's just reading the flip-flop bit, so that's just a digital read. And then to consume that character, again, we do 8 reads of D in, and we toggle the shift clock in between each read, and we just OR those together with the appropriate bit mask. And when we're done, we pulse the D in done line to clear the flip-flop so that the Z80 knows it can send us another character. All right, so that's good fun, right? But what are we going to do with it? So, well, I found an beautiful version of TinyBASIC. And this was written for the 8080, and it dates back to 1976. TinyBASIC has a really fascinating history. It was actually one of the first, if not the first, open source software projects. Lots of people developed different versions of TinyBASIC, and it spawned the growth of Dr. Dobbs' journal and all kinds of interesting things like that. So this is from 1976, right? And it was modified 2016 by Don Stewart to use in a particular Z80 computer, and so he describes nicely in here what changes had to be made. So this was pretty easy to come in and make some changes to. Now this is 8080 code, and I have a Z80 assembler, and I didn't want to translate or find another tool, so I actually ended up modifying the assembled binary code, but it was pretty straightforward to do once you get the pieces right. So and I didn't dig very deeply into this code, just enough to do what I had to do. And basically there's 2 I/O routines that do most of the work. So you have to be able to read a character and you have to be able to send a character, okay? So so reading a character is straightforward. Right now the code is set up to read from port 3, check bit 1, and if it's not set, kick out. Otherwise, read the byte from port 2 and then go ahead and mask off the most significant bit, see if it's a control O, and so on and so forth. So that was a trivial change, right? I had to read in from port FD, that's my status, still a no op. I had ANDed with 1 because bit 0 indicates whether a character is ready, still return a 0, and then if it doesn't return, I input the character from port FE. So that was just a few changes, right? Change that to an FD, that to a 1, that to an FE. And making these changes is not too bad. So So basically I had the hex file that the person who posted this provided, right? And it's got, you know, it's an Intel hex file, and it's got basically the assembled code. And so it was really just a matter of finding where line 684 was. So we can come down here, find 680. So this is a colon, this is 10 saying there's 16 data bytes on here. Here's 0680, which tells us that that's the address. Here's 2 bytes, 00, that's a flag. And then here's 80, 81, 82, 83. And there's hex 84, so that starts with a DB. And then these next bytes, 03, well, that's the 03 right here. That's the old address, right? So all I had to do was go into this file and make some changes to this. So so I created a basic mod.hex. And there, if we go to 680, we can come across, and there's the DB, that's the input instruction. But now the next byte is FD, right, which was what I needed this to change to read the status bit from my proto board, right? So so this is just a matter of you know, making a few hacks to this file, and that's how I went about implementing these changes. So other changes I had to make. I moved down the location where the code ends to 07FF just to give me some breathing room. I changed the address of this code OC2, which is what's actually used for doing output, and I changed that to location 770 hex. So in the very beginning, when it jumps to OC2, which it does after a reset 2 instruction, I changed that to jump to 770 instead of 671, right, which is the old OC2 location, or 66C. So so I had to make those changes, and then I had to write a new routine for OC2. So that came out looking like this, and it's pretty much the same as what was already in there. So this code basically it does some stuff at reset 2 to see if Control O has been pressed, and then when it's all done, if it's got output turned off, it'll pop A and F and return. Otherwise, it comes here. This is checking a status bit, check bit 1, and it spins here until it's safe to send a character, and then it pops off A and F, sends it out, and then it continues on to check if it's a carriage return. If it is, it sends a line feed, restores a carriage return, returns. So pretty much the same thing, except I needed 1 extra byte, so I had to relocate all of this down to location 770 down at the end of where the old ROM ended. So same business, right? My jump if not 0 back to OC3, which is 775, otherwise return. And then it's 775 OC3, so I read from my status bit. I check bit 1 to make sure that it's not set. And if it is set, if it's not 0, I go back and spin. So this is waiting for the UART to be ready to receive another character. And then I pop off AF, I output it to FB, and then here's the extra instruction I needed. I needed output to F7 to set the flip-flop saying that I've got a character ready. I could probably hack that in hardware, but this was more straightforward. And then I jump back to 67B, and 67B just continues with the old OC3 routine, so checking the carriage return, line feed, business, and so on. So so those changes got made, and you know, I put them into the hex file, and then I wrote this this hex to bin converter that basically just, you know, it has 64K of characters, and it reads the Intel hex file, parses it out, populates the memory array with the bytes contained in there, keeps track of the largest location in case the hex file is not ordered, and then it writes out this Z80 ASM file that my loader is used to dealing with. So so that leaves me with this basic mod.bin, which which is a pure binary file, right? It starts with a tag Z80ASM and then a control Z and a line feed and then a starting address, and then it's just the raw bytes. And those bytes just go all the way to the end, and that is a format that my loader program will ingest. All right, so that's all the setup. So here's the Z80, and it's reset and it's stopped, and you know, here's my interface to it. So I've got all of that stuff. So I can say let's choose a file, and you know, there's my basic mod.bin, and if I say load, you'll see it loads in here. It flashes when it's done, and that's it. It's loaded in 1,924 bytes. And so now I can reset it, and I can say run, and it should be off and running. All right. So so let's come over. Let's open up another terminal window. And my Arduino is on USB 1, so I can open this up, and it says TinyBASIC, okay. And you know, I can say question mark, and it'll say what, and I can say print hello, and it says hello. And I can write a little program. And let's print out hello and I squared. And let's do next I. And if I run, hey, there we go. We've got BASIC running. And it's running on the Z80. And all of this other stuff, the proto boards, the Arduino, all that, that's just a dumb terminal, basically. But a very overpowered dumb terminal. But, you know, there you go. We've got BASIC code. And we can list it and so on and so forth. You know, if I change this to 20,000 and I run, right? So Control O works, right? So you can pause output. All but it finishes really quickly if you do that. But I can pause output briefly. And, you know, while it's running, I can stop. Oh, my square got to be too big. So this is TinyBASIC, right? So it's pretty small. So I can print 32767, but if I try to print 32768, that's too big. So let's just print I, and let's run that. And so this will run for 20,000. And here you can see Control O works. There's 850, and then it continues with 1200 and so on. And you know, if I go ahead and I stop my CPU, it's stopped. And you know, I can step this, and it's going to take a lot of steps before it gets to 2021. But you know, I can say tick 100 and do that a few times. And so we're doing 100 ticks. Well, let's do 300 ticks at a time. And there's 2021, and so you can kind of see how much work is going on in the interpreter to get to the next instruction. So if I tick 10,000 times, so I don't know, something like 20,000 clock ticks maybe, to count one iteration of this for loop. And if I say run, you know, it'll continue. So this is you know, kind of cool because we can step through this, you know, one instruction at a time. And if I want, I can turn on my bus signals, and I can, you know, start ticking a single instruction at a time and see exactly what's happening here. And I can step, you know, from instruction to instruction and see where it is. And this is hardware in the loop, right? This is not a simulator. This is actually running on, you know, this physical Z80 right here, and the program's, you know, in that static RAM. But I'm tapping in and temporarily borrowing the Z80 to do things like, you know, show me what the values of the registers are and so on and so forth. And the bus signals, were coming into the processor inside this Z80 box, so I can read those signals. And one could do all kinds of things. You could add watch points. You could say, step until IO request is equal to 1, and so on. But for the most part, if you're not single stepping, if you just say run, this thing is just running just the Z80 and the static RAM talking to each other, and the processor inside here, the ATmega, is kind of out of the picture. But then when we go into stopped mode, and we start executing, this is all being governed by the processor in the Z80 box. So it has access to things like what's the current instruction, what's the program counter, and so on. So anyway, that's kind of what I've been up to, and it's just kind of a fun project. No particular reason, but it's nice to get old hardware to work. It's nice to get old code to work, and this code was written in the 70s, and it still runs today, and that's kind of cool. So, and Control C works, of course. So anyway, that's what I'm up to right now. So I need to do something better over here. Doing this proto board for serial communication is not ideal. So got a couple of projects in mind next. One, making an interface from a PS2 keyboard and a small LCD display. See if I can get rid of the Arduino and the external processor and just make a sort of standalone keyboard display interface to this. But then the bigger goal would be something like CPM, right? So re-implement the BIOS basically for doing character I/O, but also disk routines. Make some hardware support for that, probably driven by an Arduino or something, but do that and see if I can get CPM up and running on this, and that would be kind of fun. Anyway, that's what I've been doing. So so there you go. All right, thanks. Bye. Hey, so here's a follow-up using a different terminal program that's a little faster. So just reboot it, and we've got TinyBASIC running over here. And if I single step through here, you can see that we're basically in a loop, right? We keep making a call to 684. That's the check IO. It reads from port FD, and it reads in an FC. And then it ends it with a 1, and that gives you a 0, and it says return if 0. So A is 0, there's no character available. And so, and then it goes back and it makes another call to 684. And here we can actually, do some single stepping at the clock cycle level. So here's an input from FD, and you can see that it does a refresh signal, right? Because it refreshes periodically. So there's a memory request with a refresh, which is just for dynamic RAM, and then it does a memory request and read. So it's reading the second operand, the second byte, which is the operand. So that's an FD, and it reads that, and then it goes back to quiescent, and now it does an IO request and a read, and the address bus is showing FD, and that's triggering the logic on that proto board to tell it the value of the flip-flop, and then it goes ahead, it does a no-op just for filler, it does another refresh at the end of that instruction, and then it goes back to an M1 cycle, does a memory request with a read with an M1, which is an opcode fetch, so it's fetching the opcode for AND, which is E6, and then it's doing another refresh, and then it does a memory request non-M1 cycle, so this is an operand fetch, that's the 0, 1 being fetched, and that request goes off, and it's executed, and it's back to an M1 request, and now you can see A is a 0, and it's going to say return if 0. Well, it fetches the C8, that's the opcode of the return, does its refresh, and then it's going to do the return. So right now our stack pointer was FFC, and we were at location 689, and after the return, So it's popping a return address from the stack right now, right? It's doing memory reads, and it read a 1, and then it read a 5, and now it's back to an instruction fetch at location 501, and our stack pointer is FFE, right? So it popped off the return address 501, which is where it does this jump if 0 and so on. So we can dig in and we can do this low-level stuff, and that's fun for like debugging. And then I can just say run and let it continue, and I should still have TinyBASIC over here, which is you know, doing its usual thing. And one more bonus feature. So you know, can't really call a system until you've tried to generate prime numbers on it. So here's a classic prime number generator, right? So A is the number we're testing, B is the divisor we're testing, do the division. Now this is an integer machine, there's no square roots, there's no decimals, that's okay. If B is bigger than X, we know that we've exceeded the square root without finding a factor, so we go ahead and we print out A, and we go back and find the next number. If B times X is equal to A, then A divided by B must have been an integer. In other words, X is an integer, it's a factor, and so we go back and we generate a new number. Otherwise, we go back to 40 and we test a new possible factor. And if we run this, sure enough, you know, there's our prime numbers. So that's kind of cool. So yeah, prime number happiness, always a good thing. And if I remember my basic correctly, let's see if we can do this. So it used to be you could do a comma and it would print things out in columns. Yep, there we go. So there's prime number happiness. Nice and speedy, right? But you know, it's doing a ton of operations. So this is a 4 megahertz crystal driving the Z80. And you know, this was what the speed of computers was. So BASIC is interpreted, and it's running on this you know, modestly clocked Z80, typically 4 clock cycles per instruction, like a no-op, but depending on number of operands, right, you can go up to, you know, 10, 20 in some case clock cycles for one instruction. So not a whole lot of throughput, but it works. We got up beyond 1,000, so that's awesome. All right, that's enough fun for now. Thanks. Bye.